In this presentation, what we're going to do is look at the binomial distribution, and what we're going to do is derive the expected value of a binomially distributed random variable. So essentially what we're going to do is show that the expected value of x is n times p. Now, in this presentation, or this proof that we're going to use, we are going to use the binomial distribution. Okay, so it's the binomial theorem. Okay, which is, let's just treat it as something separate for the binomial distribution. But if you're on a mathematical science course, you probably should have seen that along the line somewhere. Okay, so so here we have our random variable, our binomial random variable, and the two key parameters are n and p. Okay, and this is what we're going to do. We're going to derive the expected value of x, which is n times p. Okay, so if you have 10 trials and the probability of success is 0.4, then 10 times 0.4 is 4. Okay, now the variance of x, which will follow on another time. I'm not going to do this in this video, it's probably going to be too long, but how to derive the variance of x, how to come up with that little expression. So essentially what I'm going to sort of concentrate on now is mathematically prove this part here, okay, using the binomial theorem. Now let's just start off with the basics. So this is the expected value for a discrete random variable, okay? So for each numeric outcome and the probability of that outcome, we just sum them up, and so multiply them out and sum everything up. Okay, so for a binomial distribution, okay, this is what we're looking at: 0, 1, 0 successes, 1 success, all the way up to n successes. Okay, so let's just look at that there. Okay, that's the proper formula for the expected value of x. Okay, now, so let's just sort of do that for each term. So for the first term here, 0 times, and the probability of 0 successes is, out of n trials, is 1 minus p to the power of n. Okay, so 0 times 1 minus p to the power of n. For the next one, probability of 1 success is p to the power of 1 times 1 minus p to the power of n minus 1, and so on. Okay, so this is for x equals 0, x equals 1, and so on. Now, I'm just going to sort of concentrate on this one here. That actually will work out to be 0. Okay, that would work out to be 1. That would work out to be p times 1 minus p to the power of n minus 1. Okay, but what I'm sort of focus on is this one is 0. That's sort of important. The reason we can say that is we can basically disregard this outcome in this calculation. Okay, so when I'm calculating this out, essentially I can go k equal to 1 without any loss of generality. Okay, so for n, so the expected value of x is go from, rather than k equals 0, k equals 1. Okay, now what I'm going to do here, so this is actually what I'm going to do here now is for each of these outcomes here, I'm just going to rename them k. Okay, so I'm going to first off we're going to disregard this one here, and won't cross it off completely. Let's just put a red line through it. Okay, and what I'm going to do here is just rechristen that k, just to sort of get sort of the notation that we're used to with binomial distribution, and the probability of x equal to k. Okay, yeah, so k is just all the way up to n. Okay, so rewriting that out, this is xi here, it's just k, and this is probability of xi is this part here. Okay. Okay. Just again, what we're going to do here is we're going to change this from k equals 0 to k equal to 1. Okay. So far so good. And what I'm going to do now is I'm going to focus on this bit here. K to the power k times n, choose k. Okay, I'm going to focus on that bit in particular. So there's a sort of reason why we're going to do this. Or what we're going to do is, remember, I'm trying to set something up so we can use the binomial theorem later on. Okay, so this is what I'm starting with here, and this is what I want to finish with over here. Okay, now the reason for that is that it would sort of allow me to use the binomial theorem later on. So it's not immediately clear why I'm going from what's on the left hand side to what is on the right hand side, but just to know that what is on the right hand side will allow me to simplify things greatly later on. So this is the goal we're setting ourselves. Okay, so let's just sort of take out that k there for a second. Let's just sort of concentrate on what we're doing here. So n choose k is simply n factorial. N factorial over k factorial times n factorial is n there. Okay. So when we add in the k, we have k times n factorial over k factorial times n minus k factorial. Okay. So what does that mean? Well, if we have k over, essentially what I'm going to do is look at this part here and this part here, the k and the k factorial. Okay. So what I'm going to do there, I'm rubbing stuff out when I don't mean to. What I'm going to do there is just actually state that k factorial is k times k minus 1 factorial. Okay. So essentially what we can do is simplify both of these out and essentially just try to sort of factor this out and go just write k minus 1 factorial. Okay, so interesting so far, but let's take a little bit further here. So we have k minus 1 times n minus k. Remember, what's on the bottom has to add up, okay, to what's ever on the top. Okay, just remember that. So sorry, just let's be clear about that. B factorial over A factorial times B minus A factorial. That's essentially the sort of general shape of this. Okay, so whatever is on the bottom has to add up to what's up on top. So if we add that out, we actually get n minus 1. Okay, so k minus 1 plus n minus k actually adds up to n minus 1. Okay, so essentially what we have to do is go back up to the numerator here and have n minus 1 factorial there. Essentially that's just to sort of be consistent with this choose operator. Okay, so what I'm going to do here is we're going to rephrase the numerator as, let's just go back up here. This is what we're working on here. We're going to restate that as n times n minus 1 factorial. Okay, so that is equal to, let's just put that in brackets. Okay, that is equal to n times n minus 1 factorial all over k minus 1 factorial times n minus k factorial. Okay, and essentially this part here can be written as n, well, the n times n minus 1 k minus 1. From n minus 1, choose k minus 1. Okay, so that's a sort of good bit of work there. Now it's not immediately clear why we've done that, but just if you bear with me. Sorry, what I'm going to do from now on is I'm going to write q as 1 minus p, just to make it a little bit sort of easier to read on the page. Okay, so let's just sort of recap what we've done there. We've actually sort of translated this here into that there. Okay, so that's this big step. And also p, when we use q equals 1 minus p. So what have we got? Let's just piece everything we got together. So the expected value of x is n k equals 1, okay, times n minus 1, k minus 1. From n minus 1, choose k minus 1. Now, p to the k, and we're going to use q here just to essentially just make it a little bit easier to read. Okay. Okay, now, so far so good. What I'm going to do here now is I'm going to take n and p out of it. So we have a spare n here, and what I'm going to do is we have p to the k, I'm going to replace that by p to the k minus 1 and take p out of it. So we have n times p times sum of n from from k equals 1 to n of n minus 1 k minus 1 times p to the k times q to the n minus k. Alright. Seems to be everything in order here so far. Okay. Now, if you follow what I said already, that's what we have. That's what we're looking for. So, we got a whole lot of spare stuff here. And basically, what are we going to do with it? This is where the binomial theorem comes in. So it was quite important. We're going to use the binomial theorem to get rid of all that, basically. Okay, and there's a reason why I'm sort of using Q here, where I don't usually use Q, because it just makes it a little bit more obvious what I'm doing. Okay, but first off, what I'm going to state here is that I'm going to just slightly rearrange things a bit. We're going to have n minus k here. We're going to rename that as n minus k equals n minus 1 minus k minus 1. Okay, just bear with me on that. That's sort of, again, setting up towards the binomial distribution. So just up here, this part here, we're going to replace that with n minus 1 minus k minus 1. Okay, or just keep that in mind. So what I'm going to do now is I'm going to let we're going to rename a couple of our variables. We have let n minus 1 equal to m, okay, and we're going to let k minus 1 equal to j, okay. So a bit out of the ordinary. Where did he just spring from? Okay, don't know. Okay, but essentially what we can do here is we can just replace everything here. We can sort of simplify things a lot up here, okay. And that is, oops, I went a bit too far here. I should have a k minus p to k minus 1. Okay, sorry, I overstepped the mark there. But anyway, so essentially what I'm going to do is rephrase this entire expression here in terms of m and j. So we have the expected value of x is n times p times the sum from n to j equals 0, because remember k, if k is 1, j is equal to 0, okay, and m if is n minus 1, okay. So m j p to the j and q to the m minus j. Great. This is where we get to use the binomial theorem directly. So I have it written down here somewhere. Here I have. So the binomial theorem is a plus b to the power of n. Okay. N to the k, a times n minus k and k. Okay. So let's just go back up here. So essentially what we could do is let that all adds up to a plus b to the power of n. Okay. So essentially we have it in that form here. So we can take this next step here now directly. Okay. So this all here is n times p times p plus q to the power of m. That's the binomial theorem there. Okay. Now think about this for a second. We're not trying to be getting rid of this altogether. What is P plus Q? That's P plus 1 minus P. That's just 1. So what we have here is N times P times 1 to the power of M. Oh yeah, that just cancels out altogether. So that just cancels out to 1. So what we are left with is N times P. Okay. So in a nutshell, just a couple of quick arithmetic operations. And remember, just spell it out at the start that the binomial theorem was the whole trick for this. Okay. All right.